Hey folks, how y'all doing? We are starting a new chapter today. This is chapter 4, and 4.1 is on eigenvalues and eigenvectors. These are pretty important concepts, and so I want to get started on these right away. But before we do that, we're going to start with just a little introduction as to what we're looking at and why we're looking at it. So we're going to start with this transformation, t of x equals ax, and my matrix A is this matrix right here. And our first question is, what happens with the standard basis vectors in R2? Well, we know because we've done this before that a transformation takes the standard basis E1 to the vector 4, -2, and the transformed version of E2 is 1, 1. And so that's what happens to the standard basis vectors. If I wanted to draw this out, E1 and E2 transform into these vectors here. And visually, that's kind of hard to describe what's happening. Um, it looks at first like maybe the vectors are being rotated, but they're not being rotated by the same amount. This angle is exactly 45 degrees, but this angle is a little bit less than 45 degrees because for -2, exactly 45 degrees would be about here. So the vectors are not being rotated by the same angle, and they're not being scaled by the same amount. There's some rotation going on, some scaling going on, but it seems kind of doesn't seem like there's a pattern to it necessarily. Uh, what we're going to try to do is we're going to redo this same problem, but instead of using the standard basis, we're going to look at an alternate basis. We talked about alternate bases in chapter 3. An alternate basis for R2 just has to have two linearly independent vectors. In this case, our linearly independent vectors are going to be these two vectors right here. Do they form a basis? Yes, they do. Because if I were to put these two vectors side by side and row reduce them, I would have a leading entry in both columns. I'm not going to take the time to do the row reduction. It's just one step. You can do this yourself if you want to check it. What does the transformation do to these vectors? Well, we'll do some calculation here. The transformed version of B1, we're going to apply these entries in B1 as weights on these columns. So that's 1 times the first column and -2 times the second column. So in the top row, that's 4 minus 2 is 2. And the bottom row, that's -2 minus 2 is -4. And in the second vector, B2, my weights are 1 and -1. So that's 1 times 4, -2, minus 1 times 1, 1. In the top row, that's 4 minus 1 is 3. In the bottom row, that's -2 minus 1 is -3. But let's graph this now. Let's see what happens. B1 is 1, -2, and B2 is 1, -1. And the transformed version takes these vectors. B1 goes to 2, -4, and B2 goes to 3, -3. And one of the things we notice immediately is this is easier to describe because the vectors are not being rotated. B1 scales by a factor of 2, went from 1, -2 to 2, -4, and B2 scales by 3. Uh, um, 1, -1 goes to 3, -3. And so now in this alternate basis, this transformation is just a scaling operation and not some combination of scaling and rotating. It's simpler to describe in this alternate basis. And because it's simpler to describe in this alternate basis, it will be also simpler to solve problems in this alternate basis. And later we will start to see some examples of problems that will be easier to solve using this alternate basis. But that's our idea, is that we're building an alternate basis in which a transformation is easier to describe. Um, Conceptually, this is not anything harder than U substitution. In U substitution, we make a change to a calculus formula that makes it easier to integrate. What we're doing is we're making a change to a basis that makes a transformation easier to visualize. Um, but we're going to have to do some examples before you get comfortable with this, and I understand that. But this is something you did before in calculus class. You can you succeeded then. You're going to be able to succeed against it here. So we're going to do some definitions. Um, we're looking at non-zero vectors. A non-zero vector has a magnitude and a direction. The eigenvector, an eigenvector of a matrix, is a non-zero vector whose direction is unchanged by A. Or if it does change, it flips by exactly 180 degrees. Because flipping by 180 degrees we can describe as being scaled by a negative amount. So unchanged is a positive scale. Changed by exactly 180 degrees is a negative scale. That means that AX is an exact multiple of X. For historical reasons, we use the Greek letter lambda to indicate this multiple. And so a definition, and the one that you'll find in the book, is that an X is an eigenvector of A if A times X, and this is the linear transformation, is just a multiple. This is the multiple of X for some value lambda. Um, and so if we can easily describe the transformation just by scalar multiples alone. In this case, the value of lambda is called the eigenvalue, and this only applies to square matrices. Only square matrices have eigenvectors or eigenvalues. We can't do this for a non-square matrix. All right, let's get started. Let's try some examples. So here's the matrix A, 1, 6, 5, 2. And I want to show that 6, -5 is an eigenvector of A. Well, if we apply this matrix, this vector to the matrix A, using the weight 6 times the first column and -5 times the second column, let's see what happens. The top row becomes 6 minus 30 is -24. And the bottom row becomes 30 minus 10, which is +20. This vector here is an exact multiple of the vector we started with. It's exactly, if I call this starting vector v, this is exactly -4 times v. And so this matrix affects v by just scaling it. But does not rotate it. And the second part of the question is to find the eigenvalue. Well, the eigenvalue is 4. And again, we usually use the Greek letter lambda to stand for the eigenvalue. And so lambda is equal to -4. So If I give you a vector and you want to test to see that's an eigenvector, we just multiply out this linear combination and see if the answer is a multiple of the vector that we started with. Let's try another example. Using exactly the same matrix A, show that 7 is an eigenvalue of A and find an eigenvector whose eigenvalue is 7. So the matrix we were looking at is 1, 6, 5, 2. And this time I'm not telling you what the vector is. I'm just going to call it xy. But if I apply this vector to this matrix, x times the first column and y times the second column, then the answer is an exact multiple. In fact, it's 7 times the vector we started with, 7x and 7y. Now we can solve this. The top row says that x plus 6y is equal to 7x. And the bottom row says 5x plus 2y is equal to 7y. I'm going to bring the 7x and the 7y over to the left side so that these equal 0. And so now I have x, since I'm subtracting 7x, negative 6x plus 6y is equal to 0. And 5x minus 5y is equal to 0. And if I factor out a 6 from the first equation and a 5 from the second equation, well, then I'm just looking at negative x plus y is equal to 0 and x minus y is equal to 0. And both of these equations just tell me that x and y are the same. And so give me a vector in which x is equal to y. Let's try 1, 1. Then 1 times 1, 5, and 1 times 6, 2 would be 1 plus 6 is 7, 5 plus 2 is 7, and so 1, 1 works. In fact, any vector in which x is equal to y, except that we have a requirement that the eigenvector cannot be 0. So x and y cannot be 0. So any vector in which x equals y, except for the vector 0, 0, would be a valid answer for finding an eigenvector. All right, let's try one more. This is a 3 by 3 matrix, but 2 is an eigenvalue of A. And this time we want to find 2 eigenvectors that are linearly independent and write the corresponding eigenspace. So there's a shortcut for doing this that we're going to see in a moment, but we're going to start this one out the long way. So let my eigenvector be x, y, z. And if I multiply x times the first column and y times the second column and z times the third column, the answer is going to be 2 times the vector I started with, because my scaling factor is 2 now. 2x and 2y and 2z. Well, the top row says 4x minus y plus 6z equals 2x. The middle row says 2x minus y, plus y plus 6z is equal to 2y. And the bottom row says 2x minus y plus 8z equals 2z. If I make this into a homogeneous equation by moving these terms to the other side, then I get 2x minus y plus 6z equals 0. It's a y. 2x minus y plus 6z equals 0. When I bring the 2x over here, this becomes 2x. When I bring the 2y over here, this becomes minus y. And when I bring the 2z over here, this becomes 6z. All three equations are the same. That doesn't always happen, but it happened here. Which means if I were to row reduce this, these two equations would go away, and both y and z would be free variables. So this is like 2x minus y plus 6z equals 0, y equal to s, and z equal to t. And so 2x is equal to s minus 6t, y is equal to s, and z is equal to t. And now s is multiplied by 110, and t is multiplied by negative 601. And so these are my two linearly independent eigenvectors. The eigenspace is the span, is a space, and all subspaces are spans of the vectors 110 and negative 601. As I mentioned, later on we'll have a shorter way of doing this example, but this is how we could do this example here. Again, the thing to remember is that an eigenvalue, if I plug in a vector and use that vector as the weights in a linear combination, the answer I get is the original vector multiplied by the eigenvalue. In this case, the eigenvalue was 2. All right. I want to show you what happened, though, in this example here, and where we're going to build up to this shortcut. Um, on the right side of the equation, I have 2x, 2y, and 2z. But when I combine the 2x with the 4x, this term changes, and this term changes, and this term changes, and now my system is homogeneous. We're going to make use of the fact that our changes happen on the diagonal, and the result is a homogeneous system. And we're going to build up to this shortcut that I was talking about. So let's say we have some matrix A. It's got to be square. It does not have to be 3 by 3. The matrix can be of any size. And XYZ is an eigenvector. I'm using a 3 by 3 example, but this works for any size matrix. Then the matrix times the vector is lambda x times lambda y times lambda z. If I use x, y, and z as the weights in a linear combination, this is what I get. But then when I move the lambda x, lambda y, and lambda z over to the other side, the terms that are on the diagonal are the ones that change, and then the right side is now homogeneous. So what this tells us is if we modify the matrix A by subtracting lambda from the diagonal values, and then form a homogeneous system by augmenting with zeros, then the eigenvector will be a solution. But we know even more than this, and this is where the shortcut comes in. Because the vector is non-zero, because we are requiring that eigenvectors cannot be zero, then the homogeneous system has to have more than one solution. Because the homogeneous system always has 0 as a solution, and it also has this eigenvector as a solution. And that means the system will have a free variable. it has to have a free variable in order to have a non-zero solution to the homogeneous system. And if we have a free variable, that means that the row-reduced version of the matrix will have a 0 somewhere along the diagonal. What does that tell us about the determinant of the matrix? It tells me that the determinant will equal 0. And so here's our big theorem. We have a square matrix. If we modify A by subtracting lambda from the diagonals, we call this modified matrix A minus lambda times I. And here's why this works. We know that I is the identity matrix. And so lambda times I is just lambdas along the diagonals. And so A minus lambda times I is just taking the A and then subtracting lambda from the diagonals. So that's what we're doing here. We're taking the matrix A, we're subtracting lambda from the diagonal. Then the solutions to the determinant equation are the eigenvalues of A. And so the determinant will lead us to the eigenvalues immediately. Ready to try an example? Let's do this. So I have a matrix here, and we're going to find the eigenvalues for this matrix. So we can do this. Step one is we subtract lambda on the diagonal. And that gives me the matrix negative lambda, 1, 2, 1 minus lambda. The second step is we're going to take the determinant and set the determinant equal to 0. The determinant is we multiply the main diagonal first, so negative lambda times 1 minus lambda, minus the other diagonal, which is minus 2. And this we can FOIL out. This is negative lambda times 1, and negative lambda times negative lambda is plus lambda squared. And I'm going to rearrange these terms for a second. Lambda squared minus lambda minus 2 equals 0. And this we can factor. Lambda squared minus lambda minus 2 equals 0 factors into lambda plus 1, lambda minus 2 equals 0. And so lambda is negative 1, and lambda is equal to 2. And these are my eigenvalues. So if we want to find the eigenvalues for the matrix, we start out by subtracting lambda on the diagonal, take the determinant, set the determinant equal to 0. That will get us something that we hope will factor. And if it factors nicely, that gives us eigenvalues. All right, we're working with the same matrix here, 0, 1, 2, 1. And we know the eigenvalues are negative 1 and positive 2. And the question now is to find the eigenvectors for this matrix. Okay? So these were the eigenvalues. So here's the trick for finding eigenvectors. I'm going to go back to the previous slide, and I'm going to use this matrix right here with the lambda missing from the diagonal. So the matrix from step 1 is negative lambda 1, 2, 1 minus lambda. And I'm going to plug lambda in for both of these and make this a homogeneous system. So the homogeneous system using lambda equals -1. Negative of -1 is 1. And 1 minus a -1 is a 2. That's the homogeneous system we get using lambda equals -1. Here's the homogeneous system we get lambda equals 2. -2, 1, 2. 1 minus 2 is -1. And one of the things I think you'll notice is that both of these systems will have a free variable in them. This one is easy to row reduce. We're going to just take row 2 minus 2 times row 1, and we're left with 1, 1, 0, 0, 0, 0, and the second variable is free. In the second example, we're just going to take row 2 plus row 1, 2 and -2 is 0, -1 and 1 is 0. And again, the second variable is free. We're guaranteed to have a free variable because in the previous example, we set the determinant equal to 0. And when the determinant is equal to 0, we have a system that doesn't have zero, that has a 0 entry along its diagonal in echelon form. And so that's what's happening here. In both cases, we have a free variable. So the first equation, this is x plus y is equal to 0, and y is equal to t. And so x is equal to -y, negative t, and y is equal to t. And so we get t times -1 and 1. And so the eigenvector for this first equation is -1, +1. All right, for this one, I'm going to do one more step. I'm going to go ahead and put this into reduced echelon forms. That means divide by -2. That gives me 1 -1/2, 0, 0, 0, 0. And so x minus 1/2 y is equal to 0, and y is equal to t. And so x is equal to +1/2 t, and y is equal to t. And so we get t times 1/2, 1. And so my eigenvector for lambda equals 2 is +1/2 and 1. If you don't like fractions, you can set t equal to 2. And when t is equal to 2, 2 times 1/2 is 1, and 2 times 1 is 2. And so you could also use the multiple 1, 2, sorry. This is what we get when we set t equal to 1. This is what we get when we set t equal to 2. You can set t to any non-zero value you want to if you want to get rid of the fractions. So either of these is a correct answer for the eigenvector for the lambda equals 2. All right? So the next example is using the same matrix here. We're going to use the two previous examples to efficiently compute 0, 1, 2, 1 raised to the 10th power times 5, 1. Now, when we say a matrix to the 10th power, that means we're using the column row rule on this 10 times. This matrix squared is 0, 1, 2, 1 times 0, 1, 2, 1, column row. So that's 0, 2 times 0, 1 plus 1, 1 times 2, 1, which is 0, 2 times 0 plus 1, 1 times 2. That's going to be 2 in the top row 0 and 1, that's going to be 1, 2, and 0 and 2 is 2, and 2 and 1 is 3. That's just to the second power. Question wants us to do that 10 times. We could do column row rule 10 times and get an answer. But here's the trick. I'm going to erase all of that. We know that if A is 0, 1, 2, 1, the eigenvalues are -1 and +2, and the eigenvectors are, let me just double check these, -1, 1, and +1, 2. So this is information that we have from before. What we're going to do now is we're going to find a way of writing 5, 1 as a linear combination of these two eigenvalues. So what I want to do is I want to solve this system. -1, 1, 1, 2, 5, 1. All right. I'm going to get rid of this -1 and make it a +1 by just taking negative row 1. So that gives me 1, -1, -5, 1, 2, 1. And I'll get rid of this 1 by taking row 2 minus row 1. 1 minus 1 is 0. 2 minus a -1 is 3. 1 minus a -5 is 6. So then row 2 divided by 3 is 0, 1, 2. And then I'll add that to row 1. 1 and -1 is 0. -5 and 2 is -3. What this tells me is if I take -3 copies of the first vector, -1, 1, and +2 copies of the second vector, I should get the vector 5, 1. So in the top row, I get -3 times -1 is +3. +3 plus 2 is 5. In the bottom row, -3 times 1 is -3. 2 times 2 is 4. -3 plus 4 is 1. That does check. All right. Well, we can solve this. This is the same thing as 0, 1, 2, 1 to the 10th power times this linear combination. -3 times -1, 1 plus 2 times 1, 2. But we know what happens when we multiply this matrix times this vector. It scales by a factor of -1. And so what we get here is -3 times this matrix scales by -1, and we've multiplied it 10 times -1, 1. And then this is going to be 2. And then when we multiply this matrix times this vector, it scales by a factor of 2, but we've multiplied that 10 times 1, 2. Well, -1 to the 10th power is +1, so that just goes away. And we have -3 times -1, 1. That's just 3 and -3. This is going to give us some big numbers. 2 times 2 to the 10th is 2048 times 1, 2. That's a big scalar, but that's okay. This is 3, negative 3, plus 2048 times 1, and 2048 times 2, and that's 2051 and 4093. And we have calculated this out exactly without having to column row rule this. The trick was, in this first step, we replaced phi 1 with a linear combination of these eigenvectors. And because the eigenvectors don't rotate, they just scale, then I put the scalar negative 1 to the 10th power here, and the scalar 2 to the 10th power here, and that gave me something that I can work out without having to do a lot of extra matrix work, other than the matrix work necessary to do this first step of finding this linear combination. All right, we have a few more examples to do, but this is the main point from this section, is that these eigenvalues and eigenvectors make it possible to solve a problem involving a power of a matrix without actually having to work out what that power of the matrix is. All right. So here's another example. We're going to find the eigenvalues for this matrix here. 6, negative 1, 6, 1. So the trick again is what we subtract lambda from the diagonal. And we take that determinant and set it equal to 0. And this determinant we get by multiplying 6 minus lambda times 1 minus lambda minus the other diagonal, which is negative 6. And we'll FOIL this out now. 6 times 1 is 6. 6 times negative lambda is negative 6. Negative lambda is negative 7 lambda. Lambda times lambda is lambda squared. Minus a minus 6 is plus 6 is equal to 0. When I rearrange the terms, I get lambda squared minus 7 lambda plus 12. This has a name. It's called the characteristic polynomial of A. It doesn't really matter whether you know the term characteristic polynomial, but you will see that term again in differential equations. And so if you know what it's called now, you will be a little bit of an advantage when you get to chapter 3 of the differential equations course. So, all right. So this is what we want to find, is how do we solve that? Well, lambda squared minus 7 lambda plus 12, that factors into lambda minus 3 and lambda minus 4. And so my eigenvalues are positive 3 and positive 4. So those are the eigenvalues. In the next example, we know the eigenvalues now. They're 3 and 4. The question says find the eigenvectors. So what we're going to do is we're going to use this matrix here that we subtracted lambda from. 6 minus lambda, negative 1. 6, 1 minus lambda. And we're going to build a homogeneous equation for both of these eigenvalues. So the homogeneous equation for lambda is equal to 3. 6 minus 3 is 3, negative 1. 6, 1 minus 3 is negative 2. And the homogeneous equation for lambda is equal to 4. 6 minus 4 is 2. 1 minus 4 is negative 3. All right. Let's row reduce these. I'm going to get rid of this 6 by taking row 2 minus 2 row 1. 6 minus 3 is 0. Negative 2 minus 2 times negative 1 is negative 2 plus 2, and that's also 0. And so the second column is free. Over here, we're going to row reduce this by taking row 2 minus 3 times row 1. 6 minus 6 will be 0. And negative 3 minus times minus is plus 3 is 0. And again, this column is free. I'll divide by 3 and 2 here. This gives me 1 negative a third, 0, 0, 0, 0. And this is 1 negative a half, 0, 0, 0, 0. And this tells me that x minus a third y equals 0 and y equals t. So x equals 1/3 t and y is equal to t. And so we have t times 1/3 1. We can use that, or we can multiply. We can plug t equals 3 in and use the vector 3, 1 instead of using 1/3 1. Not 3, 1. When I plug in t equals 3, 3 times 1/3 is 1 on the top. 3 times 1 is 3 on the bottom. I'll get that right. 1, 3. And then this is the same idea. X minus a half y equals 0, and y is equal to t. So x equals 1/2 t, y equals t. We could use 1/2 1, or we can scale that to 1 and 2 by multiplying everything by 2. And I like to use the scaled versions because I prefer not to use fractions if I don't have to, but it's perfectly okay to use 1/3 1 if you would rather use 1/3 1 here. All right, we now have the eigenvalues. They're 3, 4. And the eigenvectors, they're 1, 3, and 1, 2. The next question says to compute this matrix raised to the k power times 2, 5. So again, our previous information, lambda is 3 and lambda is 4. And my vectors are 1, 3 and 1, 2. So I want to come up with a combination of 1, 3 and 1, 2 that adds up to 2, 5. So if we take row 2 minus 3 row 1, 3 minus 3 is 0, 2 minus 3 is negative 1, 5 minus 6 is negative 1. Now this, I'll take out a negative sign. 1, 1, 2, 0, 1, 1. And the top row now, I'm going to take away row 2. 1 minus 1 is 0, 2 minus 1 is 1. And so it just turns out that one of each vector is all we need. 1 times 1, 3 plus 1 times 1, 2 does indeed add up to 2, 5. So there's our linear combination. So 6, negative 1, 6, 1 to the k power times 2, 5 is the same thing as 6, negative 1, 6, 1 to the k power times 1, 3 plus 1, 2. I'm leaving out the ones this time because they don't make a difference. And when I multiply this times 1, 3, it scales by 3 each time. So we get 3 to the k times 1, 3. And when I multiply 6, negative 1, 6, 1 times 1, 2, it scales by a factor of 4. And we've multiplied it k times. So 4 to the k times 1, 2. Well, that's in the top row, 3 to the k plus 4 to the k. In the bottom row, 3 to the k times 3 is 3 to the k plus 1 plus 2 times 4 to the k. And we have an answer, and we never actually had to multiply this matrix out k times. All right, let's keep going. We're going to compute this product here. So we're going to do all of this work that we've been spacing out onto separate slides. We're going to try to do this all on one slide now. All right, so we're going to find the eigenvalues. That means we subtract lambda from the diagonal. Okay, so when we multiply these together, we get, we want the determinant of this. So this is negative lambda times 1 minus lambda minus 6. That's negative lambda plus lambda squared minus 6. Or if I rearrange terms, lambda squared minus 6 equals 0. That factors into lambda plus 2 lambda minus 3. And so my eigenvalues are negative 2 and 3. So those are my eigenvalues. So now we're going to find the eigenvectors. And this requires looking at two homogeneous systems. The first one, we're going to plug in negative 2 here. Minus a negative 2 is 2. 1 minus a negative 2 is 3. And the other system, we're plugging in 3 here. Negative 3, 6, 1. 1 minus 3 is negative 2. All right. I'm going to switch the two rows here and put 1, 3 in the top row, 2, 6 in the bottom row, and take row 2 minus 2, row 1. That gives me 1, 3, 0, 0, 0, 0. And so x plus 3y is 0, but y is equal to t. So x is negative 3t and y is t. And so negative 3, 1 is an eigenvector. Over here, we're going to switch rows again. So I have 1, negative 2, 0, negative 3, 6, 0. Row 2 plus 3 times row 1 is 1, negative 2, 0, 0, 0, 0. And so x minus 2y is 0, y is 0, y is t. So x is equal to 2t and y is t. And so 2, 1 is an eigenvector for this part of the problem. So then for the third part of the problem now, computing this, I want to find some combination of these two eigenvectors that adds up to 1, 8. So we're going to now take negative 3, 1 and 2, 1, augment that with 1, 8, and see what we can do. I'm going to switch rows again. And take row 2 plus 3 row 1. 3 and 3 is 0. 2 and 3 is 5. 1 and 24 is 25. Take row 2, divide by 5, and that's going to give me 1, 1, 8, 0, 1, 5, and then row 1 minus row 2 is going to give me 1, 0, 3, 0, 1, 5. So what should be the case is that 3 times the first column and 5 times the second eigenvector adds up to 1/8. Does that check? In the top row, we have negative 9 plus 10 is 1. In the bottom row, we have 3 plus 5 is 8. So that does check. So that means that this product here is also this product. I'm going to replace 1/8 with this combination. 3 times negative 3, 1, plus 5 times 2, 1. And that's not a 6, that's a 4. It's the exponent. When I multiply this matrix times this vector, it scales by a factor of negative 2. And when I multiply this matrix times this vector, it scales by a factor of 3. But again, we're raising this to the 4th power because we did this 4 times. All right, a little bit of calculation here. Negative 2 to the 4th power is 16. 16 times 3 is 48. Times negative 3, 1. 3 to the 4th power is 81. 81 times 5 is 405. 48 times negative 3 is negative 190. No, it's not. What is it? 48 times 3 is negative 144. 48. 405 times 2, 1 is 810. 405. When we add these together, 810 minus 144 is, let's see, 6. 6 and 6. 666. I did not plan that, but that's how it turned out. And 48 plus 405 is 453. And that's the result that we get. So there's a lot going on here. Finding the eigenvalues, then finding the eigenvectors, then finding the linear combination that unlocks this problem, and replacing the 1/8 in this problem with that linear combination. But once we have done that, this exponent becomes less of an obstacle because we're not taking a matrix to a power, we're just taking a scalar to a power. And therefore, even for very large exponents, this method can be efficient. All right. Last problem, and this is going to segue into what we're looking at in the next video. We want to find the eigenvalues for a matrix that's in echelon form. Well, the eigenvalues, again, we want the determinant of this matrix. The matrix we get when we subtract from the diagonal, 5 minus lambda, negative 7 minus lambda, 19 minus lambda, 1 minus lambda, and 4 minus lambda. We want that determinant to be 0, but in echelon form, we can just multiply this down the diagonal. And this is a polynomial that's already factored for us. And so lambda is equal to 5, or lambda is equal to negative 7, or lambda is equal to 19, or lambda is equal to 1, or lambda is equal to 4. And so diagonal matrices, and matrices in echelon form in general, but especially diagonal matrices, have nice special properties when we talk about eigenvalues. And that's going to lead us to a process called a diagonalization that will let us solve even more complicated problems than the ones we solved today. I've got to go ahead and wrap up. Thank you for staying through this video. I know it was a long one. Y'all take care. Bye-bye.